We're continuing our discussion of how Clifford algebras can be used to build spinors. In a previous video, I said that we can define spinors as members of minimal left ideals in Clifford algebras. We've already defined what a Clifford algebra is, and in this video I'm going to explain what a minimal left ideal is. In the first part of this video, I'm going to talk about projectors, which are also called idempotents. And in the second part of this video, I'm going to talk about how projectors lead to ideals. I'm also going to give the definitions of some algebraic structures, like rings and algebras, along the way. So let's begin by talking about projectors, which are also called idempotents. I'll start by talking about projectors used on vectors, and this should match up with your common sense idea of what a projector does. Afterward, I'll use this idea to explain projectors in Clifford algebras, which is a little more abstract. Let's say we have a vector v and some xy axes. And let's say I want to project this red vector v onto the x-axis. This would mean we project v down along this dotted line onto the x-axis, so that only the x component remains. If I wanted to project this red v vector onto the y-axis, we project v across this dotted line onto the y-axis, so that only the y component remains. Now, let's say I've projected a vector onto the x-axis, and I want to take the result and project it onto the x-axis again. Our new result after the second projection is unchanged. It's the same vector we already started with. So the conclusion here is that doing a projection once is the same thing as doing that projection twice. Converting this into symbolic language, if we have a projector P, applying P once should be the same thing as applying P twice. So P equals P squared. This is the mathematical definition of a projection operator, also called an idempotent. Let's look at some examples of matrix projectors. This matrix here projects out a 3D vector's z component. It sets the x and y components to 0 and leaves the z component alone. You can check that this matrix squares to itself, so applying it once is the same thing as applying it twice. This other matrix projects a 3D vector onto the xy plane, so that the z component is set to 0 and the x and y components are left alone. This matrix also obeys the same projector property. Now let's consider something else. Let's say we've taken a vector and we've projected it onto the x-axis. Now let's take the result and project it onto the y-axis. The result is that there's nothing left. We get the 0 vector. The conclusion here is that when we project a vector along two different orthogonal directions, we get 0 as a result. We say that two projectors P and Q are orthogonal if applying one and then the other gives us 0. The two matrix projectors we showed earlier are orthogonal. If we project onto the z-axis and then project onto the xy plane, there's nothing left and we get 0. And as expected, when we multiply these two projection matrices, we get the 0 matrix. If we were to project onto the xy plane and then project onto the x-axis, the result is non-zero, so these two projectors are not orthogonal, and they do not multiply to give us the 0 matrix. Let's look at some projector properties. If we have a projector P, then 1 minus P is also a projector. In the language of matrices, we can think of 1 as just being the identity matrix. We can show that 1 minus p is a projector by showing that 1 minus p all squared equals itself. As an exercise, you can try pausing the video and proving this property, as well as other upcoming properties, before I give the answer. After we distribute, p squared becomes p since p is a projector. And here, minus p and plus p cancel with each other. This gives us 1 minus p, which is the original projector. So this shows that 1 minus p is a projector. As an example, if p projects onto the z-axis, then 1 minus p would be the identity matrix minus p, which gives us this projector onto the xy plane. We can also prove that the projectors P and 1 minus P are always orthogonal to each other. We prove this by multiplying the two projectors and showing that we get 0. After distributing, p squared becomes p, and p minus p equals 0. Indeed, the projector onto the z-axis and the projector onto the xy plane are orthogonal and multiply to 0. Here's another property. If p and q are orthogonal projectors, then p plus q is also a projector. Again, we can prove this by showing p plus q all squared is equal to itself. After distributing, the p-q product terms go to 0 because they are orthogonal. And p squared equals p and q squared equals q since they are both projectors. And we get p plus q as desired. So for example, a projector onto the x-axis and a projector onto the y-axis are orthogonal. But if we add them together, we get a new projector onto the xy plane. Finally, I'm going to give a definition. A projector is called minimal if the projector cannot be written as the sum of other projectors. So the xy plane projector is not minimal because we can write it as the sum of other projectors. But the projectors onto the x and y axes are both minimal projectors, because we can't write either of these as a sum of simpler projectors. We'll see later in this video that minimal projectors are related to minimal ideals. So to sum up, a projector is an operator P with the property that p squared equals p. Two projectors P and Q are orthogonal if PQ equals 0. Each projector P has an orthogonal projector partner 1 minus P. The sum of two orthogonal projectors is another projector. And a projector that can't be written as the sum of other projectors is called minimal. Also, projectors are also called idempotents. Idempotent is just a fancy word for something that doesn't change when you apply it multiple times. Now, what we've seen so far are matrix projectors that act on vectors. This should be pretty familiar to anyone who knows linear algebra. Next, I'd like to talk about projectors in Clifford algebras. Specifically, we'll look at projectors in CL30, which has basis vectors sigma x, sigma y, and sigma z that all square to +1 and all anti-commute with each other. A member inside a Clifford algebra P is called a projector if p squared equals p. Let's take any unit vector u in CL30. Because vectors in Clifford algebras square to their squared length, u squared equals 1 because it's a unit vector. The expression 1/2 times 1 plus u is a projector. We prove this the usual way by showing that it squares to itself. We distribute, and since u squared equals 1, we get 2 plus 2u. Factoring the 2 out, we can cancel it with one of the factors of 1/2. And we get 1/2 times 1 plus u, which is the original projector as desired. I'll call this projector Pu+. Its orthogonal projector partner, 1 minus Pu+, is given by 1/2 times 1 minus u. I'll call this projector Pu-. So any arbitrary unit vector u in a Clifford algebra will give us a pair of projectors, Pu+ and Pu-. As a specific example, we can look at the z unit vector, sigma z. If we look at the 2x2 matrix representation of the sigmas, we know that 1 is just the 2x2 identity matrix, and sigma z is just the z Pauli matrix, with entries 1, 0, 0, -1. This gives us these two projection matrices for pz+ and pz-. Let's take these projectors and apply an arbitrary 2x2 matrix to them from the left. We see that pz+ has the effect of projecting out the first column and setting the other entries to 0. Likewise, pz- has the effect of projecting out the second column and setting the other entries to 0. Notice that if we add these two projections, we get the original matrix back. This is because when we add the two projectors together, we get 1 back, which is the identity matrix, which doesn't change anything through multiplication. So when we add the two matrix projections together, we can factor out the original matrix and sum the projectors to 1, which gives us back our original matrix. Now, here we've been looking at the 2x2 matrix representations of projectors in CL30. Now let's look at abstract members of CL30 written out using symbols. So given any arbitrary multivector element M in our Clifford algebra, our projectors pz plus and pz minus can break M up into two pieces. I'll call these two pieces mz plus and mz minus. We can then add the two pieces back together to get the original M, since pz plus and pz minus add to give 1. The same is true for any pair of orthogonal projector partners. They can always be used to break up elements into two pieces that can be added back together again to give us the original. Let's switch gears for a bit and talk about ideals, which is a concept that comes up when studying rings and algebras. Loosely speaking, a ring is a set where addition, subtraction, and multiplication are all defined, but we don't require division to be defined. For example, the integers form a ring because we can add, subtract, and multiply them to get more integers, even though dividing two integers doesn't always give us an integer. Matrices also form a ring because we can always add, subtract, and multiply matrices. Division with matrices would be defined as multiplication with a matrix's inverse. But since not all matrices are invertible, we can't always do division with matrices. But that's okay because division isn't required in rings. The definition of an algebra is a vector space where addition, subtraction, and multiplication of vectors are all defined. But we don't need division between vectors to be defined. Addition and subtraction come for free in vector spaces, but vector multiplication is something extra that needs to be defined. Clifford algebras are considered algebras because the Clifford product allows us to multiply vectors. The wedge product from Grassmann algebras also allows a vector space to become an algebra. Now let's talk about ideals, which are special subsets of rings and algebras. An ideal is a special subset of a ring or algebra that's sort of like a black hole, because ideals suck other ring elements inside of them so that they can't escape. I'll show you what I mean. Let's take a look at the integers. Specifically, we'll look at the subset of integers that are multiples of 3. So -6, -3, 0, +3, +6, and so on. The multiples of 3 are like a black hole because, once we get inside, it's difficult to escape. Adding any two multiples of 3 together will always give another multiple of 3. For example, 3 plus 9 equals 12, or 18 plus -3 equals 15. Also, multiplying any integer by a multiple of 3 gives us another multiple of 3. For example, 7 times 3 equals 21, and -5 times 3 equals -15. So the multiples of 3 are a special subset of the integers that's sort of like a black hole. The sum of any two members in the set gives a result that's still in the set. And the product of any integer with a member of the subset will result in another member inside the subset. The generalization of this pattern gives us the definition of an ideal. An ideal I is a subset of a ring or algebra where the sum of any two ideal members gives us another ideal member, and the product of an ideal member with any other element gives us another ideal member. The multiples of 3 form an ideal inside the integers because they satisfy both of these properties. We can also look at ideals with matrices. Let's look at this subset of 2x2 matrices where only the first column is non-zero. This is an ideal inside the ring of 2x2 matrices. If we add two matrices of this form, we get another matrix with only the first column being non-zero. Also, if we multiply a general 2x2 matrix from the left onto a matrix of this form, we get another matrix where only the first column is non-zero. So these matrices form an ideal. Note that this multiplication trick only works if the general 2x2 matrix is multiplied from the left. It doesn't work if the matrix is multiplied from the right. For this reason, we call this subset a left ideal, since the multiplication property is only satisfied if multiplication is done from the left. If we look at the set of 2x2 matrices where only the top row is non-zero, this ends up being a right ideal, because the multiplication rule is satisfied only when matrices are multiplied from the right. It turns out that any set of matrices with only specific columns being non-zero form left ideals, and any set of matrices with only specific rows being non-zero form right ideals. So we have this abstract definition of ideals, but what do these ideal sets really represent inside an algebra? To help give an intuitive understanding of what ideals mean, I'm going to use a kind of metaphor or analogy. You shouldn't take what I'm about to say too literally, but it will hopefully help you understand what ideals mean. In mathematics, it's often useful to take a complicated object and cut it up into simpler pieces. For example, if we have a three-dimensional vector space, one way to cut it up into simpler pieces is to introduce some xyz axes. This allows us to take a vector and break it up into a sum of x, y, and z components. When it comes to rings, ideal subsets are sort of like the axes of the ring. They allow us to break up members of the ring into smaller, more basic pieces. For example, in the ring of 2x2 matrices, we can break up a generic 2x2 matrix into two pieces. One piece where only the first column is non-zero, and one piece where only the second column is non-zero. Each of these pieces represents a left ideal subset, as we showed earlier. These ideal subsets are sort of like the axes of our ring. We can add pieces from our ideal subsets together to get any arbitrary 2x2 matrix. We could also break this ring up into right ideal subsets, where only the top row is non-zero and only the bottom row is non-zero. This can be thought of as a different pair of axes for breaking up our ring members into ideal components. Now, this axis metaphor doesn't work for all ideals. For example, it does not work for the multiples of 3 inside the integers. But the metaphor does work if our ideal is connected to a projector. And here's where we get to the main point of this video, where we bring projectors and ideals together. If we find a projector inside our ring or algebra, it turns out that if this projector acts on the entire ring or algebra, the resulting set will be an ideal. In other words, every projector in a ring creates an ideal. Recall the two projectors we defined in the Clifford algebra CL30, which were pz plus and pz minus. When we multiply a matrix M onto pz plus from the left, we get a matrix where only the first column is non-zero, which is an ideal subset. And when we multiply a matrix M onto pz minus from the left, we get a matrix where only the second column is non-zero, which is also an ideal subset. So each of these projectors creates an ideal subset. If we take the two projected ideals and add them back together, we get the entire original space of 2x2 matrices. This is again related to the fact that pz plus and pz minus add together to give 1. If we act on these projectors from the right instead, we get the top row ideal and bottom row ideal instead, which are right ideals. Let's go ahead and prove that projectors lead to ideals. Recall that an ideal subset must satisfy this addition property and this multiplication property. Let's take a ring R with two orthogonal projectors P1 and P2, where P1 and P2 add to 1 and multiply to give 0. We get the set I1 from multiplying the ring R onto the projector P1 from the left, and so I1 is a left ideal. Let's first prove the addition property. Two ideal members must add together to give another ideal member. If small r and small s are members of the ring, then Rp1 and Sp1 are in the set I1. Basically, any member multiplied onto P1 from the left is defined as being inside the set I1. Adding these elements together gives us small r plus small s times P1, which is also in I1 by definition. Now let's prove the left multiplication property. Left multiplying any ring member onto an ideal member gives us another ideal member. If small r and small s are members of the ring, then Rp1 is in the set I1. If we multiply from the left by small s, we get small s small r times P1, which is also in the set I1 by definition. So this proves that I1 is an ideal. The same reasoning can be used to show that the set I2 equals r times P2 is an ideal. Now, an important fact is that two ideals, I1 and I2, share no members except 0 if their respective projectors are orthogonal. In other words, the intersection of ideal sets I1 and I2 is just the 0 element. This makes sense with our axis metaphor of ideals, where the only place two axes intersect is the origin, or 0. However, this is just a metaphorical picture, and we still need to actually prove this is true. Looking at our ring R, the ideal I1 is a subset inside of R. If we take a bunch of ring elements and project them using projector P1, they will all end up inside the ideal I1. Let's take this element AP1 and give it the name small r. Remember, projecting twice is the same thing as projecting once. So projecting the ideal member AP1 again does not change its value. In other words, projecting an ideal member small r does not change its value. Now, let's assume a ring member small r belongs to two orthogonal ideals, I1 and I2. So projecting r using P1 doesn't change its value, and projecting small r using P2 also doesn't change its value. So small r P1 equals small r P2. Multiplying both sides by P1 on the right, P1 squared gives P1, and P2 times P1 gives 0, since they are orthogonal. So this means the projection of small r is 0, which means that small r itself is 0, since small r was already in the ideal. This completes the proof that the only member I1 and I2 have in common is 0. So the metaphor of axes for ideals is a decent visualization. The only element that the axes have in common is the origin, 0, and the only element that ideals from orthogonal projectors have in common is the ring's 0 element. Finally, note that it's possible for some ideals to live inside other ideals as subsets. Loosely speaking, this is similar to how we can project onto the xy plane and also project onto the x-axis. But the x-axis is a subset of the xy plane. If an ideal has no sub-ideals inside of it, we call it a minimal ideal. Minimal ideals correspond to minimal projectors, which are projectors that cannot be written as a sum of other projectors. Let's summarize everything we've learned in this video. Projectors are operators that square to themselves, and two projectors are orthogonal if they multiply to give 0. Ideals are special subsets inside rings and algebras that are like black holes, because ideals suck other ring elements inside of them so that they can't escape. Addition and multiplication always bring us back inside ideals. Finally, we learned that there's a correspondence between projectors and ideals. And a projector that acts on a ring or algebra will always give us an ideal subset. When we have a set of orthogonal projectors that all sum to 1, the resulting ideals act like a set of axes for our ring or algebra. They break up the ring or algebra into its most basic components. Adding elements together from different ideals gives us more general members of the ring or algebra. Finally, minimal projectors are projectors that cannot be written as a sum of other projectors. These correspond to minimal ideals, which have no ideal subsets inside of them. We're going to see that elements of minimal left ideals in Clifford algebras correspond to spinors. In particular, the 2x2 matrices with only the first column being non-zero behave essentially like the Pauli spinors we saw used in quantum mechanics and the Jones vectors used in classical optics that we saw in videos 2 to 5. However, I'm going to need another video to explain this. So in the next video, I'll show how spinors are members of minimal left ideals in Clifford algebras.